Alrighty, so we're just going to look at an example of style of question we might get given. So this is actually 6.1 question 1. Okay. So they've given us a function x brackets x minus 1 squared and asked us to find the stationary points and identify all the key features of this function, and then later on we're going to be asked to graph it. So before we go any further, it's always a good idea to ask yourself, well, what do we know about the function fx? So looking at that function straight up, I can see that I've got something. It's going to be x squared times x, which means we're dealing with a cubic, and it's going to be a positive cubic as none of those values there are negative. Okay, so we've got none of the values at the front, so none of the x values are negative. So we've got a positive cubic applying here. We also know that we have x-intercepts, and if you look at the graph, sorry, not x-intercepts, yes, x-intercepts, they occur on y equals 0, and the only point in time where this function will equal 0 is when x equals 0. So we've got x-intercepts at x equals 0 and x equals 1. Now there's a little hint, because normally a cubic would have 3 intercepts, but the fact that we've only got 2 tells us that there might be something going on at one of these intercepts here. Okay, so we know that it's a cubic, we know that it's positive, which means it's probably going to look something like this. Okay, so our function will look something like that. So I'm looking for some turning points at some point. If I was studious and I watched the last video, I'd know that I was probably expecting 2 turning points. Okay, but I may not get 2, but I'm expecting to see, I should see 2. So before we go any further, I want to now try and find my derivative function. So fx equals x minus 1 squared. Now I could expand it and do it all individually, but I'm not going to do that. I want to use my set of rules that I've learnt throughout the term. I want to use my product rule, because I've got a function multiplied by a function. I'm going to let u equal x. I'm going to let v equal x minus 1 squared. U dash is quite simply 1. V dash, okay, I can use the chain rule, or I could use the chain rule shortcut. In this case, I might just, I'll do it properly. Okay, I'm going to let the inside equal, I just want to do the shortcut, 2x minus 1 is what that's going to equal to the power of 1, which is obviously just 2x minus 2. Okay, so that's where I'm at. F dash x equals u v dash plus v u dash. Okay, shove my values in. X times 2x minus 2 plus 1 times x minus 1 squared. I can see there I get 2x minus 2x squared minus 2x plus x minus 1 squared. I'm going to expand that just to make it a little bit easier. 2x squared minus 2x plus x squared minus 2x plus 1 equals 3x squared minus 4x plus 1. I'm pretty sure that's my derivative function. Okay, so as you can see, my derivative function here is starting to look a little bit like a quadratic. So I need f dash x to equal 0, which means that 0 equals, just tilt it up a little bit more, 0 equals 3x squared minus 4x plus 1. Okay, immediately I can see that I've got a quadratic. I've got 2 options. I can create my set of brackets like so, or I could use my quadratic formula. I'll just see how we go here. They're going to have to be minus 1, minus 1. Okay, they're the values I get. So in that scenario, either that equals 0 or this equals 0. So x equals 1 or x equals, I should do that under the right one, x equals 1 on 3 or x equals 1. Okay. they're the values I get. I'll actually take a bit of time and show you how I got that. Alternatively, so for that to occur, either 0 equals 3x minus 1, or 0 equals x minus 1, which means that 3x equals 1, or x equals 1, that side's done. I'll just do it the other side so it looks a bit nicer. So x equals 1 over 3, or x equals 1, so they're the two possible values. If I couldn't quite get this part on my own, I obviously have the option, because it's tech free, I have to use my quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, and my two answers of that will give me my x value for that. Pretty cumbersome and you're likely to make a mistake, so probably try and avoid doing that if possible, and try and use the factorisation of that quadratic. So I've now got my two values for my stationary points. I need to know a little bit more than that. So I know when they're going to occur. I now need to know what value of y I'd be expecting. Okay, so if I come over here, know that, and I'm going to rub this off because I don't need it anymore. I know that my function's got stationary points at 1/3 and 1, so I probably want to find out what the y value of those points are. Actually, before I do that, I want to find out whether I've got a max or a min. So, to find out whether I've got a max or a min, I use a big table. Now, this is what we saw in the last video, but to get this table, I'm actually going to make it nice and big this time. fx x. Again, I don't care about the size of the numbers. What I care about is whether they are positive or negative. Now, I'm going to shove my values of 1 on 3 and 1 in there, okay, because I know these points are 0. So they're my stationary points. Now I just want to know what occurs between those stationary points before and after. So I'm going to pick a point. I'm going to let x equal 0. That's always a nice value to let it equal. Okay, and if I look over at I'll just put a little reminder about what our f dash x function is. F dash x equals 3x squared minus 4x plus 1. Okay, so you can use that as heavy you'd like, or you can use the brackets over there. Either way, when that equals 0, I've got a positive value, which tells me my function is going to look like this. I'm going to select a value of a half and select a value of 2. Why not? Okay. So if I've got a half, I haven't got a calculator, so I'm going to try and do this without a half. I've got f dash of a half, sorry, equals 3 over 4 minus 4 over 2 plus 1, which equals negative 5 over 4 plus 1, which equals negative 1 over 4. So that gives me a negative value. Okay, I'm going to do exactly the same thing again, but I'm going to change my value. I'm going to go f dash of 2, which equals 3 times 4 minus 4 times 2 plus 1, which equals 12 minus 8 plus 1, which equals 5, which doesn't matter what it equals. All I need to know is that it's positive. Okay, so now if I rub all that out, I can see my function goes positive, negative, 0, positive, which tells me on my graph this is my max, this is my min. So if I go back to my stationary points, I know that x on 1/3, that's my min. I know that x of 1 equals my max. Sorry, other way around. 1/3 equals my max, 1 equals my min. Now if we look at this graph, and I'm just going to try and quickly draw this below these points. If we look at that graph, we can see pretty clearly. So it's going to look something like this, right? where that is x equals 1, that's 1/3. We don't know what our y value is, but we can find that out very shortly. But we can see that this point here is clearly not the maximum function. And we can see that the other point, x equals 1, is clearly not the minimum. So if we continue that function beyond to infinity, we can see that they won't be the maximum functions. That's why we give these guys a special name. They're called the local max and the local min. And what that's saying is around that area, they are the max and the min values. Depending on your domain, depending on your function, you may be required to use those. Okay, but just for now, be aware that we're still finding the maximum. We call it a local max or a local min for a cubic function. Just be aware of that. The next video, we'll find the y values of that and get to describing what that function looks like in curve sketching.